record. All right, so we have just started discussing about limits, and we're right where we need to be. I planned a little bit of time lapse between the sections just in case accidents like the one yesterday, technology accidents happen. Um, so I am going to continue discussion about limits. Now, there's one thing that we didn't discuss. So there's actually two things that we didn't discuss from that section, and I want to emphasize today. These are questions that are in the homework assignments. Remember, the homework assignments are in your syllabus. And I invite all of you to go through these problems. I do not necessarily solve all the problems in class, but I will try my best to go through as many as possible. Whereas, per my promise, I do about half of your homework questions here in class as examples, and then you do the remaining half at home. Now, that's an approximate number. Never going to be able to hit exactly half, folks. So whether sometimes we do 40%, sometimes 60%, and so I'm going to try my best to do as many as possible here in class. But before we do so, let me actually share a screen with you. So where is my screen thing here? Oh, here. All right, let me share this screen with you. So I'm going to share the whiteboard, and oops, no, I don't clicked on the wrong button. All right, so there we go. Click on that. So I'm going to share the whiteboard with you, and I will just want everybody to remember that the essential thing we discussed here was the numerical approach to calculations of limits. So in class last time we did something like, and boy, let me see if my pen is working. So, oh, just my pen somehow. All right. So, 1 second, folks. Oops. Oof. Now having now another problem with the. All right. All right. I'm going to write with the mouse for a moment. It seems like I'm having a small pen problem over here. All right. So not a major issue though. We are going to calculate yet another example of a limit. So instead of sharing this board, let me share the Desmos anyway. I was going to Desmos, but I'm going to write directly in Desmos. So I am going to share the following example with you. And the example that I'm going to share with you, folks, is going to be the following. So over here, I'm going to calculate, and as we said earlier, so let me write a note here. So by the way, again, as a reminder, so if you want to do something, write something in these boxes or some sort of special formula, a table or something, you click on the plus sign here. So what I did, I clicked on the note symbol. All right. So I'm going to write here, calculate. Oops. Okay. So that doesn't do the thing that I said. There we go. Calculate the limit as x approaches. And I'm going to do, for my promise, a problem from the book. And that problem will be, so let's say this one here, number 19. So x approaches, I'll write in the notes in a second. The x approach is 3 and the expression is a bit complex here. So in order to write this expression nicely, I'm going to write it with parentheses here, and then I'll plot it in Desmos. X squared minus 3x. So I have x squared minus 3x divided by x squared minus 9. I'll write that in a second in with nice formulas, but for the time being, because I'm taking notes here directly in Desmos, it's gonna look kind of ugly like that. So what I'm gonna do again, I'm gonna copy this formula that I put here. I'm just gonna do a Control C because I'm on a Windows machine, and then I'll say Control V here, and that's gonna give us the desired fraction. Now I don't like the way it is written here, so let me write it with. All right. So if we do, oops, okay. So x squared minus 3x. Let's put that. All right. You know what? I'll write that again. Sorry about that, folks. A bit of a technical mishap here. X squared minus 3x divided by, oh, there we go, divided by x squared minus 9. All right, so we need the limit as x approaches 3. So for the time being, I'm just gonna leave the graph there. But what I'm gonna say here, like we did last time, f of x equals x squared minus 3x divided by x squared minus 9. You know, we don't need those parentheses there. So there we go. So this is the function that I want to study. Remember, the limit as x approaches 3. So, so do let me know if there's anyone here who got confused. You know, there's some small technical trouble at the beginning here, but that was resolved. So, so here's what they tell us in the book. In the book, so I'm looking. This is problem. By the way, this is problem. So, so let me write in the notes here. Okay, I'm gonna write a note here to myself. This is problem, and this is problem 19. From section, and the section is 1.5. All right, so this is problem 19 from section 1.5. It's one of your homework questions. Now, the thing with this problem is to calculate that limit, they say to do a table. And they tell us what kind of table to do, and I am going to do the exact same thing. So I chose, again, I clicked on the plus sign here, on the plus symbol here, folks, and I chose the symbol. I chose a symbol. Where is the symbol? The symbol is this table here. And I clicked on that. So Ali, maybe if you don't have a question, maybe you wanna turn off the microphone. So you seem to have your mic on, and I can hear some background noise. All right. So oh yeah, Ali, that's just click on. Yeah, there we go. All right. So thank you. So there we go. So folks, over here, just remember to switch the letters. I clicked on the wrong thing. So this is t, and this is going to be f of t. So we're going to do a table of values for this particular function, and we're going to substitute some values. And they tell us a bunch of values here. So look at these values here, because this is important. So they say do 3.1. So right now I'm just typesetting, folks. Do 3.1, and then in the next thing, so say x equals 3.1, then the next one is 3.05, and the next one is 3.01, 0.01. One second, so let me just wipe out that. Oops. All right, so we got that, and I'm going here, and I'm gonna turn off the graph here. All right, so so you can see that what this does, it plots the corresponding point t comma f of t, or x comma f of x if you want here. So that's not all though. So there's more here. So then they say do 3.001, and that's another point there, 3.0001. So 3 zeros the next one. So 3.0001. There we go. So what do we see here about these numbers on the left side? The values of t, where do they go? What number do they approach? With the values of t, I'm saying here. So the ones on the left side in the left column. So you can you can type that in the chat. So this is kind of one good thing about this Zoom. It has the chat function where you can type at least simple answers. So please type that in the chat, or turn on your mic and you can tell me here. So where do these what value do these numbers on the left approach as we do 3.1, 3.05, 3.01, 3.001, and so on. All right, so anybody who wants to say something, please say that here, folks. All right, so these values are approaching. You're saying 5? No. That's true. That's true. The values of f of x do approach 5. Well, actually, close that. So essentially, correct answer, but with a little bit of care. So, but I'm talking about the ones on the left, the ones where I have my mouse on, folks. See these that I move my square above. So I'm not really sure what you see on the other side of the wire, but these numbers here on the left, folks, approach, yes, that's correct. They approach 3. So 3.1, 3.05, 3.01, 3.001, 3.0001. The corresponding numbers in the right column here, the values of f, approach, and you can look at my mouse. It's a bit shady, the color there, so I'm not sure if you can see it clearly. But the points on the right approach not 5, but something related to 5. So what number do you think you can say there? So you can typeset that in the chat. So Liam, do you want to correct your answer? So it's not 5. What is it, the correct answer? Or somebody else? 0.5, folks. Yes, that's correct. That's correct. So it's 0.5 here. So you can see that it's 0.5081, whatever, then 0.504, then 0.5008, then 0.50008, and so on. So it's really getting closer and closer to 0.5. So we can say that the limit is 0.5. But guess what? So very good, very good. So it's kind of visible actually here. If you look at these points on the graph here, so the y value is really that 0.5. You can see my mouse on the screen. All right, but I'm not particularly interested in that at the moment, rather than doing that. So let's see what else they say in the book, in the problem, because this is an interesting problem, and this is the type of example that I want to work on. They say also choose these other values. So let's choose these other values in the table, and these are the values 2.9, and the next one is 2.95, and the next one, you know what? Instead of doing this, sorry about that. So I'm just gonna delete this thing here. And I'm going to say, wait a second, I'm not gonna write these in this table, but I'm gonna redo the table and I'm gonna list the other values in a separate table. It should be the same one here, but since I have the luxury of, I can afford the luxury of drawing 2 tables, I can do that. So I'm gonna do yet another table, so a little lower. I hope you can all see it here. So then again, I'm going to change letters. So it's going to be T, and it's going to be f of t here. All right. And that's, you know what? I'm going to wipe out the, let's change that. Let's change the letter to A and f of A or something like that. So he doesn't like that we're using the same letter. So I'm going to do A and f of A. Again, a different name for the letter. So this one of the drawbacks of this particular program is that it doesn't like the letter X. So if you use the letter X, you have to be very specific just to define functions and things like that. And then as you mix letters, it doesn't like you to mix letters. So anytime you do something different, you have to choose a different letter. So I'm going to choose a different letter. I'm going to call it A. It doesn't really matter as long as it's not X or Y or T, like you see in the previous example, or F. and I'm going to give values to, I'm going to do the exact same thing. So A and f of A, and I'm going to give values to A, the ones that are at the bottom of the page here in the book. So 2.9, 2.95, that's going to be one of them, and 2.95, that's going to be the second one. And then it says here, do more, 2.99. And that's going to be the third one, and then it's going to be 2.999. So 2.999, that's the fourth one. And finally, 2.9999, and that's going to be the fifth one. All right, folks. So, so once we got these values, look here, something interesting happens. So it's the same problem, the same function. It's just that these values here, what happens? What can you say about these values on the left? If you go 2.9, 2.95, 2.99, 2.999, 2.999, what value do these numbers approach the A's, the left column here in the table? So what value do these numbers approach? The ones that I'm running my mouse over right now. So, so where do these guys go? You can answer in the chat, folks. All right, so there's a couple of answers. So they all approach 3. Yes, indeed. So so look at these values on the left side here. So focus on the left side in both tables. So in both tables on the left side, we approach 3 on the left side. And but the difference is that I'm using numbers higher than 3 in the first table, and over here I'm using numbers lower than 3 in the second table. So, so the theory of limits would be that if I do so, I should see the same type of behavior for the values in the right column. So in other words, is it true that the values in the right column approach 0.5? And that is fairly obvious true. So, so it's fairly obvious it's true. So look at these numbers on the right side, 0.491, 0.495, 0.499, 0.4999, 0.49999. All right, so these numbers approach 0.5 as well. And we can say here, folks, we can say, and you can look on the graph to see what happens on the graph here. So look here, so the numbers in the first table correspond to points on the graph of that function on the right side. Why is it on the right side? Because 3.01, 3.001, 3.05, and so on are numbers over here to the right of 3 on the x-axis. So that's these numbers in the left column are represented by numbers on the x-axis. Remember, so so the values of x and y, x comma y, that's a point. That's what we plot here. On the other hand, the values in the left table here, and the second table, the values on the left, these represent numbers also on the x-axis here, but numbers less than 3. They still approach 3, but they approach 3 from the left side as my mouse moves here on the x-axis. From the left side of 3, you approach 3 over here. So, so these numbers, folks, that are plotted here, you can see 2.9 and 0.4915. That's the first number here. The numbers that are plotted here approach, you know, a common value here, which is 3 comma 0.5. They approach this common value from the left, and these blue numbers, blue points, approach 3 comma 0.5 from the right side. So what we did here, folks, is called side limits. Side limits. And what we got here is side limits from both sides. We say the left side and the right side, because there's only 2 directions on the x-axis. It's either coming from the left or coming from the right, right? So there's no other way to move along a line. So towards a point. So if I represent the point, let's represent the point 3 comma 0.5. Well, that point is a green point here, and that's going to be right here where these other points congregate. So what happens here, right above 3, there's where all these points congregate. The blue ones and the red ones, they all congregate there. So that's why that's the notion, that's the meaning of a limit, you know, in a graphical interpretation. Now the points, again, the red points here represent the left limit approach. We say a left limit approach, and the points on the right, the blue ones, represent the right limit approach. So we're gonna say here, and I'm gonna write in words, we're gonna say that the limit, oops, let me write a note here to myself. Oops, not that, okay. Nope, I don't want to do that. All right, I clicked on the wrong button. So we're going to say here that the limit as x approaches 3 from the right side, limit, okay, is equal to 0.5. And also the limit, so let me just copy these things. So let's write another note, the limit. I'm just going to say, I'm going to just, you know, I'm kind of lazy. So I'm just going to copy Control C and paste it here, Control V. Okay, the x approach is 3 from the left side is also equal to 0.5. So if that's the case, because we just calculated, folks, we just use points that come from the left, so and come from the right, and in both cases, the limit is that 0.5. So we're gonna say that the limit at 3 exists because the two side limits, the two approaches, are so they all points converge towards the same value, and that value is 0.5, or the green point on the graph. So this is the notion of a side limit. And now side limits, I'm going to write that here. So I'm going to write on the whiteboard now. So the side limits, all right. So the side limits, I'm going to write with the mouse because my pen seems to be, oops. All right, side limit. So I apologize, my pen isn't working properly. My tablet, this pen is not working properly for whatever reason. So when one works, the other doesn't. But we can carry on the instruction here without any problem. So the side limit, folks, is denoted like this. The limit. Let me write with capital letters so you can see better. So I'm going to say limit. RLIM here, so as x. And for the side limit, when you come from the left side, people usually write something like this: x approaches, and they put a northeast oriented arrow like this towards 3. Really, that's not necessary to do like that, because in the book, and then you got f of x here, and in the book, folks, they say instead of that, they will say limit, and they will say in the book as x approaches 3, but instead they will put an exponent here, and they will say minus, which means that x is less than 3. So I give values to x less than 3 of my function f of x. So that is the limit, the notation that they use in the book. Now, generally in math books, if you look in other books, you will see this other notation, the one that I put here with a northeast oriented arrow, that meaning that it's increasing towards 3. But for whatever reason, your book likes this style of notation. This is, by the way, this is French style notation. I don't know why he uses that. It's the author of this book is Canadian, so that might be the case. Why this might be the reason why he uses this kind of formalism. It's sometimes confusing because people confuse this minus in the exponent with -3. It's not the same thing. It's totally different. So when you see, folks, x approaches 3 from the left side, you wanna pay attention. So with that 3 in that minus in the exponent, it means you give values to x less than 3. So that's what it means. So be careful with that. So which corresponds in our table, and I'm going to go back to our table quickly here for a second, which corresponds to this table here, the second table here, where we gave values to x like 2.9, 2.95, 2.99, 2.999, 2.999. You can see that all these numbers are increasing towards 3, but strictly less than 3. And we concluded that the corresponding value of a limit is this number 0.5. So that is the situation. I'm going to go back to the whiteboard, and that is the left limit. And for the right limit, so in other math books, you will see something like this. X is descending towards 3 of f of x, or you can see also things like, and this is what you see in your book, but pay attention because it doesn't mean that that 3 is a plus. So 3 plus, when you see there 3 plus, just remember that that simply means that x is supposed to be approaching 3 from the right side, going down towards 3. So that's a story with a side limit. So I want everybody to understand. Now it so happens that in my case, both of these limits were 0.5. But you may wonder, and that would be a legit question: is it possible that that these side limits are somehow uneven, unequal? And of course it is possible. So most formulas, however, so let me just get this out of the way before I give you an example of some exceptions. Most formulas that you will need in calculus will be nice functions. I told you, functions essentially formulas, right? So will be nice functions that are pre-cooked, where you don't have troubles with these limits, with these side limits. They're usually equal, so most of the time. But there would be, an occasional situation when they're not equal, and then you have to be more careful when you treat the function. So I'll give you an example. Go back to Desmos. I have to go back because you cannot if I don't lead you there. All right, so let's go back to Desmos together, and I am going to click off all these things here just to clean up the screen here. And I'll give you an example where the side limits are not equal. And there are several examples. This is an example that uses a piecewise defined function. Why not? Since we learned them, let's use them. So this is where piecewise defined functions are very useful to build examples of functions that don't have equal side limits, or sometimes they don't even have any side limits. I'll give you an example of that. So let's do a piecewise defined function. And if you weren't here when I discussed those, here's how you write them. So let's say my function is, and I'm going to give you an example also from the book. There's a piecewise defined function here. This is number 11. So again, let me delete that for a second. You don't have to delete that if you are following this experiment in Desmos on your screen. You don't have to delete that. So I'm gonna say here, this is problem 11 from section 1.5. We do problem 11, and over here I'm gonna define the function, and the function is, I'm just gonna copy the formula from the book. So the function is this one, 1 plus x if x is less than -1. So I'll say, again, remember the condition x is less than -1 comes first, then you put a colon, and you say the formula, which is 1 plus x. All right, so let's make this. Let's zoom out. All right, so you can see that it already plots the thing there. Then you say comma, and then the next formula. In the next formula, I'm going to go again to the book. -1 less than or equal to x less than 1, x squared. All right, so the next thing is -1 less than or equal to x less than 1 period x squared. All right, so look at that. So it plotted the function for me. I don't even have to worry about plotting things here because this does the thing for me. And finally, if x is greater than or equal to 1, I have a formula 2 minus x. So I'll say comma x greater than or equal to 1. I said that. And I'll say period, colon, and the formula was 2 minus x. I'm just looking at the book. I have a book over there on my left. And look at that. That's my function. By the way, I didn't do a very good job here. I apologize, folks. So I should have said, instead of x greater than or equal to 1, which is fine, so Desmos understands that, you might want to say 1 less than or equal to x, kind of flip the writing there, but it's irrelevant. So right now, I'm going to leave it the way it is. All right. So let's see what happens with this particular function. So if we do a table of values, which points, which limits here. So I'm going to say here a note to myself. So limit as x approaches a, some unknown number a, does not exist. So that means when you might have limits from the left and from the right, but they're not equal. They're not equal at that point. That means that the limit, the overall limit, doesn't exist because the left and right side don't match. What do you think those numbers A would be? Where is it that I can calculate the values of x? I can put the values of x approaching from the left, and then I substitute and I can calculate the values of f of x, and then I do the exact same thing from the right, and I don't get equal values for the limit. Which values on the x-axis do you think I have to look at in order to make sure to kind of find a counterexample of a place where the limit doesn't exist? They're not equal from both sides. So you can tell me in the chat, and maybe you wanna explain your reasoning as well, folks. Where is it that the limit would not exist, or the values approaching from both sides would not be equal, the values of all right, so somebody says at -1, somebody else says at 3. All right, well, let's see what happens. All right, so so at -1, so let's calculate the limit as x approaches -1. First of all, that's my first thing, my first target. And I'm going to place a table there. And like I did before, I'm going to put a t here, and I'm going to put an f of t here. And I'm going to put numbers less than -1. So I'm approaching from the left first. So can you tell me a bunch of numbers that are less than -1, folks, so I can start writing here? You can tell them in the chat. So a bunch of numbers less than -1, but relatively close to -1. Where can I start? So let's see in the chat. Anybody has any ideas so we can sub those in here? So again, we need a bunch of numbers less than -1, -2, -1.5. That's correct. Yeah. So let's put -2 here, then -1.5. There we go. How about let's get closer to -1. Can somebody tell me how to get closer to -1, folks? But still to the left, right? So any other ideas? What number would I put here, which is even closer to -1, folks? -1.05. That's correct. -1 point. Yeah. -1.05. -1.05. 0, 1, and negative 1.01. We said 1.001. All right, so all these numbers here, folks, all these numbers, if we look, very good examples. So look at this. You know that you did the correct job because all your numbers appeared on the left side of the graph. The left side of the graph is, by the way, this line here. So there we go. So we did a good job. And it looks like these numbers, if you look at them. So look at this. This is the first one that you plotted, and this is the second one. And finally, there's a third one and a fourth one and so on. So, so all these numbers, as you can see, as you approach -1, so the limit, I'm going to write here a note in decimals. So the limit as x approaches -1 from the left is, and please let me know what that is. What do you see from the table here? It looks like it's what, folks? You can tell me in the chat. So what is the value that we're approaching f of t? What values do these numbers on the right side approach? They do approach 0. Yes, that's correct. They do approach 0. So we can say here that the limit from the left is 0. All right, and now let's do the exact same exercise. I know it's a bit tedious, but that's important to do this at least once in your life. So let's do the exact same exercise, a new table, a new variable name. So what did I do? Oops, my table disappeared. Okay, so that shouldn't happen. All right, folks, so a new table. Let's try table again. There we go. I think I erased too much. Not T, we said that doesn't like T. Let's put A now. So let's put f of a here. And do I invite you to play with Desmos, folks. This is a really cool piece of software. So let's give values to a here. So we want to approach -1 from the right. So basically, we want to be on this side of a graph, the green, the whole thing is green. We want to be on this side, the green side of the graph. So let's see. If we, what values should we give to x to approach, again, -1 from the right side, so coming down towards -1. What values are coming down towards -1? You know, I'm going to get you started. So here, I'll put 0. 0 is to the right of -1, right? So now let's get closer and closer to -1. So what value would you want to put next? You can tell me in the chat. So give me a couple of values that are closer to -1, but to the right of -1. All right, so somebody said here, let's see, -0.5. Yes, that's good. That's correct. -0.5. How about another one? Very good, Sammy. So there's who's that? There's Shervy, and then so I'm not sure it's Shervy. It's a he or a she. So I can't. All right. So he, okay. So he says. So Shervy says this is a negative 0.99. So there's. Oops. Nope. I didn't do the right thing. So I didn't put the right thing there. All right. Thank you, sir. So so negative 0.99. So look at this. So this number is really close to -1. Let's actually look at the graph here. You can see, oh, it's oops, negative. Where is that? The other one. Negative. What did I do? There's something wrong here. I put point. Oops. I should have put negative. There we go. Oh, look at that. So my point is really close here. Not to the left of -1, so still to the right, but very close to -1. And really, this is kind of as good as you can do. So if you want, you can do negative 0.9999 with a lot of things there, and that's going to place a point which is even closer. But the thing is, and very good folks, everybody who answered really, if we get closer and closer to -1 from the right side, my values here approach what number? My values on the right side. So in the right column, that is. So my values approach 1. That's correct, folks. So we're going to say here that the limit, oops, and I'm going to write a note here to ourselves. And this is the answer. Very good, folks. This is the correct answer. So the limit as x approaches -1 from the right is 1. All right. So in this case, folks, we're gonna say that the limit does not exist. The overall limit. So we have side limits. We have side limits. One of them is 0, and the other one is 1. Uh, at the point, right at the point -1, we have side limits, but they're not equal. So then we're going to say that the limit does not exist. Now let's see what happens on the graph. On the graph, folks, because this is important, saying that we calculate limits from the left, it means that we allow a point on the graph, and I don't want to click on that thing, so we allow the blue points to get closer and closer to so their x coordinates, their x coordinates are getting closer and closer to -1 from the left, and the corresponding points on the graph they turn out to get closer and closer to this point here, which is a -1 really comma 0, and the y coordinate of that point is my limit. You can see that my limit here is 0. The y coordinate of this point over here where all these blue points congregate, that is the limit. So remember the y coordinate. The same story happens from the right as x approaches -1. So in other words, the x coordinate, the first entry of these the values on the left column here approach -1 from the right. The corresponding points on the graph, they slide towards, they congregate towards this one here at the top of a green branch that's coming from the right, and that point has a y coordinate of 1. That's why the limit from the right is equal to 1. So that being said, folks, we're going to say that the two side limits exist, but the overall limit does not exist. This is actually the only point on the graph here that does not have a limit, because all the other points, wherever you look on the graph, if you want to do 3, like somebody suggested to do 3 earlier in the example, if you want to do 3, try do 3, plug in points from the left and from the right, and you will see that in both cases, the value at 3 will be whatever point I have here right at 3. And that point, to figure it out, will be 3f of 3. And that turns out to be, oh, all right, there's my point here. So it turns out that the value at the limit at 3 will be this y coordinate will be -1, folks. It will turn out that way if you plug in numerical values for x from the left and from the right. You will approach this point here, and the y coordinate of that is your limit. So folks, this is what I want you to get from this particular lesson. The idea that limits can be calculated from both sides, and those are called side limits. And for my limit to exist, it has to be that limits from both sides match at that point. So on a graph, the limit from a left side and the limit from the left side and the limit from the right side are correspondingly the y coordinates of the points where the points on the graph from the left side and the right side congregate. So they don't necessarily need to congregate at the same point. In this case, for example, the example where x is -1, when you congregate, when you come from the left, you congregate towards this point on the x-axis. When you come from the right, you congregate towards this point on the right, so right above -1, which is -1, 1. So the y coordinate is 1. All right. for all the other points on the graph, whenever you come from the left and from the right, you congregate towards the same point. So folks, to spot the points where a function does not have a limit, you have to spot the jumps, the breaks in the graph. So where you cannot continue drawing the graph. If you come from the left and you try to draw the graph on the screen, you will see that you go this way like my mouse goes, and you stop here, and then you have to make a jump to jump over here to continue drawing the graph. But then once you get past that point, you don't have to make any further jumps. So everything else is smooth. So there's going to be a limit there. All right. So again, points where the limit doesn't exist, look for jumps on the graph. All right. Now, there's further examples that I would like to do, but we don't have much, we don't have more time left today. What I'm going to do, I'm going to put a couple of questions from limits, like the ones that we did here today and the ones that we did last time. So mostly numerical approach to limits. So I want to see that you understand how to numerically calculate limits. You can certainly use Desmos on the quiz. And then I'm going to put some questions from the review. I will send you a batch of questions to look at before the quiz for Friday. So Friday, we will not have, well, we can actually, let me stop the recording here because, okay, stop the sharing makes the file to begin with.